All right, in this third lecture for today's set, we're going to talk about plane wave reflection at normal incidence. In the previous lecture, we looked at oblique incidence on an interface, which is actually a more complicated case. We're now going to look at the special case of normal incidence, when the wave is coming in and its direction of propagation is perpendicular to the surface. It's a little bit simpler, and we want to be able to understand what's going on at normal incidence, maybe with a little greater depth. We have three learning objectives for this lesson. The first is to be able to describe the reflection process at normal incidence. So you need to be able to apply the Fresnel reflection and transmission formulas at normal incidence, and we'll see what those are. We'll develop them here. And we want to understand how to describe polarization for the normal incidence case. Second is understanding power balance. So we want to be able to describe the power flow both on the incident side and the transmitted side of the medium, and be able to describe propagating and standing waves that may occur in each of the two interfaces. And one of the other key elements that I'd like you to be able to try to do would be to relate how these processes for plane waves are similar or different from the processes in transmission lines. So in the normal incidence case, we're going to assume that we have an incident plane wave propagating in the plus z direction, as we see here. Right? We're going to have our polarization be in the x direction. And since the electric field is in the x direction, the magnetic field will be in the y direction, so I get propagation in the plus z direction. The same will hold for the transmitted case. The reflected wave is polarized in the x direction, as we see, but since it's propagating to the left, it will be have its magnetic field into the plane of the board to get leftward propagation. I've got two media. I've got mu1 epsilon on the left, mu2 epsilon 2 on the right, and of course I have eta 1 and eta 2, which I can compute once I know mu1 epsilon. Now, importantly, when we had oblique incidence, we needed to decompose our field into two components, the TE and the TM case. But now we have the issue that our incident wave vector is in the z direction and our surface normal is in the z direction. So there's no longer a plane of incidence that's described by these two vectors, since these two vectors are parallel. And hence, for a problem on an interface between two simple media, there are no preferential polarization states. And in fact, at normal incidence, for an interface between two simple media, the problem is not polarization dependent. It is polarization independent. Well, Snell's law tells us that that theta reflected is equal to 0, right, which means it's propagating back in the minus z direction. So cosine theta incident equals cosine theta reflected, and that's equal to 1. And the reflection and transmission coefficients that we derived from the Fresnel formulas in the previous lecture reduced to this simpler example, where I have the wave impedance in medium 2 minus the wave impedance in medium 1 over the wave impedance in medium 2 plus the wave impedance in medium 1. If you wanted to, you could derive this formula directly from continuity of the tangential electric and magnetic fields at the interface. And I encourage you to do that if you'd like. But at this point, we can use our previous result and just simply state that theta incident equals 0, theta reflected equals 0, theta transmitted equals 0, and I end up with this particular formula. Notice the reflection coefficient for TE and TM are the same, which again tells us that the problem is not polarization dependent. A couple of important things. When eta 2 is greater than eta 1, so when the impedance in the second medium is larger than the impedance in the first, then the reflection coefficient is positive. And when the impedance in the second medium is smaller than the wave impedance in the first medium, then the reflection coefficient is negative. And this is very important when we'll look at the standing wave pattern in a couple of slides. One thing I want you to take note of at this point is that this relationship is very similar to the reflection coefficient on a transmission line, where gamma equals ZL minus Z0 over ZL plus Z0. Right? So that's the reflection coefficient for a transmission line, where I have a transmission line of characteristic impedance Z0 terminated by a load impedance of Z sub L, or equivalently a transmission line of impedance Z0 that then connects to a transmission line of impedance Z sub L. And we see there's a great similarity between these two properties, right? And that's because on a transmission line, I've got a planar wavefront. It happens to be a non-uniform plane wave in general, so it's a slightly more complicated plane wave. But as we're going to see in Lecture 8, we'll see that it's what we call a transverse electromagnetic mode, and it has all the same characteristics, propagating characteristics, as a plane wave. So next thing I'd like to do is I'd like to take a look at the field distribution in this case. So on the left-hand side, in this slide, over here on the left, we have incident fields and reflected fields. Right? So here are my... All right, now let's take a quick look at what the distribution of fields are in the two media. So on the left, in medium number 1, we've got the total field, which are given by the superposition of the two fields. And I've written this as a scalar, so the polarization is in the x direction. We have the incident fields plus the reflected fields. Right? I can gather my terms here. I can factor out this coefficient. The whole problem is going to scale with the amplitude of the incident field. And what I'm going to do here is a trick that we'll often do in trying to analyze things to get some physical intuition as to what's going on here. If gamma were equal to 1 or -1, then I'd have either a cosine or a sine. But in this case, gamma is not. And so what I'm going to do is I'm going to try to write this in a way. And so I'm going to add a gamma e to the minus j beta z and subtract a gamma e to the minus j beta z. So I've added and subtracted the same component, one here and one here. So I haven't changed the equation. But this allows me to group my two equations in this particular way, right? So that I've got this superposition here. So the incident field times 1 minus gamma, which is propagating to the right, plus a standing wave of amplitude 2 gamma. And let's look at a very specific example. On the left, I've got free space, and on the right, I've got a medium with dielectric constant 2.25. It corresponds to the dielectric constant of glass at optical frequencies. And if I plug this into my reflection coefficient, I get gamma equals minus 1/3. Right? So that's the value that I get for this particular problem. So here on the left, we see that I've got this partial standing wave pattern. Notice the amplitude. This is the magnitude of E, right? So I'm going to have a cosine wave underneath it. But this is the magnitude of the electric field evaluated at any given point. At the interface, I have a value of 1 plus gamma. So at z equals 0, right? So at z equals 0, this goes away. This becomes 1, and I have 1 minus gamma plus 2 gamma. So I get 1 plus gamma. At z equals 0, I have 1 plus gamma. Right? But our gamma was a negative number. Right? So 1 plus gamma will be 1 minus 1/3. Right? I've written it here as 1 minus the absolute value of gamma, because the absolute value of gamma is always positive. So we see that this corresponds to 2/3. Right? And I'm going to have this oscillatory behavior, where I get a minimum. 1/4 wavelength further back, I'm going to get a maximum. Another quarter wavelength further back, so half a wavelength, I'm going to get a minimum. I plotted here my axis in units of wavelength. So this minimum is at the interface. This next minimum is 1/2 wavelength away from the interface. Okay. We recognize these two terms as the superposition of a traveling wave and a standing wave. Right? So I'm going to have something that I compute as a standing wave ratio, just like we did in the transmission line, where I could take the maximum minus the minimum, maximum plus max plus min over max minus min, right, to get what my standing wave ratio is. The magnetic fields have a slightly different expression. The magnetic fields, instead of having E incident propagating to the right plus gamma E incident propagating to the left, I have E incident over eta propagating to the right minus gamma E incident over eta propagating to the left. And that's because my electric field in both cases was assumed to be in the positive x direction. So for the incident wave, I have to have polarization in the plus y direction for the magnetic field. And for the reflected wave, the magnetic field is in the minus y direction. Right? And so I get this minus sign here. When I gather my terms, I end up with a slightly different expression. Instead of 1 minus gamma plus 2 gamma cosine, I end up with a 1 plus gamma times the exponential minus 2 gamma cosine. At the interface in this particular case, then, when z equals 0, I have, at z equals 0, I'm going to have 1 plus gamma minus 2 gamma. So I end up with 1 minus gamma. But remember, gamma was a negative number, right? Gamma was minus 1/3. Right? So 1 minus gamma will be 4/3, or 1.33333. And we see that my magnetic field has a maximum at the interface. My electric field has a minimum at the interface. 1/4 wavelength away, my magnetic field has a minimum, and my electric field has a maximum. And then another 1/4 wavelength away, I have an electric field minimum and a magnetic field maximum. So the standing waves for the electric and the magnetic field are actually out of phase with each other. And you saw this in standing waves on a transmission line as well. So the properties of propagation on a plane, for plane waves that are normally incident are the same as you get on a transmission line. Finally, we want to take a look at what happens in medium 2. In medium 2, I use the transmission coefficient, but in medium 2, I've only got one wave propagating to the right. There's no reflected wave. So in the incident medium, I have incident and reflected. But in the transmitted direction, I've only got the fields here. And when I take the magnitude of the field, the magnitude of this exponential is 1, and I get a flat line everywhere. And you'll notice, though, and this is important, that the tangential electric field and the tangential magnetic field are both continuous across the interface, as the boundary conditions dictate that they have to be. Let's now look at the power flow in the two media. Right? In medium 1, my electric field is given this way by this expression. My magnetic field is given by this expression. Right? So I have these two things. And in medium 2, my electric and magnetic fields are given this way. Notice in medium 1, I'm using wave impedance 1. In medium 2, I'm using wave impedance 2. Here I've got the reflection coefficient. Here I've got the transmission coefficient. We know how to compute the time average pointing vector. I just take 1/2 the real part of E total cross H total on the two sides of the interface. On the left, when I gather out my terms, I've got, here I've got an e to the minus j beta z that will be multiplied by an e to the plus j beta z when I take the complex conjugate. So these two terms are going to give me e squared over eta 1. Right? And these two terms are going to give me gamma squared E incident over eta 1. And here I'm writing down with the assumption that gamma is purely real. This should actually become an absolute value. On the right-hand side, when I do this cross product, it's straightforward, and I get these two exponentials are going to cancel when I take this complex conjugate, and my transmitted power looks like this. By conservation of energy, the total power flow on the left, incident plus reflected power, must be equal to the total power flow on the right. So at the interface, I have continuity of power flow. So that means that on the left, 1 minus gamma squared over eta 1 must be equal to tau squared over eta 2. And I've chosen to write it using this particular expression. So this is a relationship between gamma and tau, which tells us about power conservation. So that brings us to a close on this lecture. In the tutorial, we're going to take a closer look at this relationship between normal incidence reflection and reflection on a transmission line. We're going to take a look at some specific cases of power flow and total field distributions for interfaces that are high impedance interfaces or low impedance interfaces and a perfect conducting interface. And we're going to take a look at this conservation of energy relationship that I just gave you.